start this program. As you know, this particular event, Neutron Star collisions at a distant galaxy, created tremendous excitement among the scientific community. So, three of us from the Astroparticle physics we try to highlight some of the important observational and theoretical aspects of this Neutron Star merger in a binary. So our first speaker is Pratik Majumdar, and I request our colleague Amit Ghosh to chair the session.
Good morning all. 17th of August 2017, in my opinion, would remain as kind of a landmark date in astronomy and astrophysics for at least many years still to come. It might get superseded by something else later. Primarily because before this date, our knowledge of the universe was somewhat, about the sources of the universe was about somewhat compartmentalized in different wavelengths and through different messengers. Primarily we used to look at our universe through optical, UV, infrared and X-rays. Then later on in the 1960s and 70s it started through looking at gamma ray astrophysics. And then you also know that in 1987 a supernova explosion took place, which is a very famous supernova explosion took place in Large Magellan Cloud, which gave us kind of the birth of neutrino astrophysics, SN 1987A. And then later, we also learned about the emission of gravitational waves from black hole mergers. But none of these observations were actually geared to look at the same source in different wavelengths or through different messengers. That is why this is except partially the 1987A, because in 1987A it was also looked at, it was first discovered in optical and in infrared, and later on it was found out that apparently neutrinos were also, the discovery that neutrinos were emitted from supernova 1987A came a little later, because the analysis and everything took place a little later. But what I'm trying to say is that it was not coordinated, it was not an effort, the efforts were very disjointed. This is probably the first time when coordinated efforts took place in order to learn about the source. So that's why I say that this is kind of a dawn of multi-messenger astrophysics, when, as you know, kind of that a merger of neutron stars in a binary system gave rise to something what is called gamma ray bursts. And I will cover a little bit the observational part of what happened in gamma rays, in low energy gamma rays, in high energy gamma rays, in optical X-rays, and then also in neutrino. So what did the gravitational wave observatories hear? Till now we were listening to most of, we were seeing most of these things, but then we had to hear some. But here I would also ask you to recall the Hull stellar pulsar in 1987, which was the first binary neutron star which was discovered, where the first evidence of that gravitational waves would exist and was kind of established, which also predicted that the shrinking of an orbit would take place, of that binary orbit would take place at about 3.5 meters per year. That predicted that neutron star collision would happen, this binary neutron star collision would happen at about 300 million years from that date. But that's a long, long story. So what did gravitational wave observatories hear on this 17th of August? At around 12:41:04 UTC, they heard was at a signal to noise ratio of 32.4, which is one of the largest of the gravitational gravitational signals that have been heard till now, there are two masses, binary masses of the range from about 0.86 and 2.26 solar masses were colliding with each other, and then they produced gravitational waves. And that's kind of the frequency versus time merger plot, where you see that at time equal to 0, there was a signal, a strain amplitude which was kind of recorded in their data. Now, independently, let me just tell you that Fermi was looking at the same position in the sky. It was kind of by chance, because Fermi goes around the Earth, and the Fermi's position was around here, between Africa and South America somewhere. This is an area which is called the South Atlantic Anomaly, we call it. South Atlantic Anomaly is a region, that's why it's kind of shaded like this, and I'll tell you why it is shaded like this. It's a region where the Earth's magnetic field is weakest, which means there is a high concentration of charged particles there. And because of that, Fermi, if you would know, that has two types of detectors. One for low energy gamma rays, which is what we call the gamma ray burst monitor, and the other one for high energy gamma rays beyond 1 GeV. This high energy gamma ray detector have to be switched off, is actually generally switched off when one passes through the South Atlantic anomaly, because otherwise the detectors may get destroyed or damaged due to high radiation. The anti-coincidence shield, which protects it from charged particles, doesn't really work that well when it enters the South Atlantic anomaly. So that's what happened, that when Fermi was just entering there, the LAT, which is the large area telescope, which is for high energy gamma rays, was switched off. However, the gamma ray burst monitor was still on. If it would have gone into the darker region, probably the GBM would also have been switched off. It would not have been able to record. So it was kind of lucky. It's a lucky coincidence that it was looking at, it was passing through that region and had not fully entered the South Atlantic anomaly. Just a brief overview of what the detectors are in gamma ray burst monitor. They are sodium iodide and VGO are used as detectors. The energy range, which are the most important things here, is from 8 keV to 30 MeV. Its field of view is very large, 9.5 steradians. The onboard localization, that means as soon as it sees a gamma ray burst, it can locate it to about 15 degrees in error. That's the onboard software does it. Whereas later on, the final offline localization, it depends upon what angle and where from it's coming. It's about 3 to 5 degrees roughly. So about 2 seconds later, exactly later it was found out 1.7 seconds, but about 2 seconds later at 12:41:06 UTC, Fermi independently actually, without any trigger from gravitational wave, found out a gamma ray burst in that area, in the region where. This is the region. They did not know where the localization perfectly was. So this is the light curve of Fermi, that you see the event rate counts per second as a function of time. And this is when the merger had happened. This is, of course, done later. The merger had happened. And this is about 2 seconds later, the GRP was located in gamma rays in Fermi. You see it has two detectors, as I said, NAI and VGO. NAI, the sodium iodide, is for the low energy, very low energy part, between 10 and 50 keV, and 50 to 300 keV is the VGO one, which is there. The luminosity they measured, they can calculate the luminosity, is about 1.6 times 10 to the power 47 Hz per second, which is about 2 to 3 orders of magnitude lower than normal gamma ray bursts. Or this gamma ray burst lasted for about less than even a second. About half a second or slightly more than half a second. So about 2 orders of magnitude lower than the normal gamma ray burst, short gamma ray burst that Fermi normally observes. So it's generally, since it's a little bit of a fun talk, I have to say a bit of stories. So it turns out the Fermi GBM PI, Colleen Wilson, she was on her way to office from some gym or somewhere, that's what it's written, when she got a phone call from the LIGO headquarters mentioning that she should look at some gamma ray bursts in the direction which Fermi had already located, and they should be looking at it much more carefully because there's something interesting going on there. And somebody from the Integral Space Station, which is another, it's a European gamma ray satellite, integral one, is also woken up by phone calls or emails, I don't know. And let's look at, and they had also, and integral also incidentally was very near in that region, and so they reported. Let me first tell you what integral, what's the energy range of integral. It uses high purity germanium detectors. Energy range is between 20 keV to 10 MeV. Its aperture is about 30 degrees, and then it has some coded mask which restricts the field of view to about 16 degrees or so. So integral, so here is the light curve from integral. This is again the gravitational wave signal, and it's about 2 seconds later. The delay here is not 1.7 but about 1.88 seconds. I don't know how great the resolutions are. I haven't looked at the paper so carefully, but anyway, within 2 seconds, almost a temporal agreement between the gravitational wave and the short gamma, this gamma ray burst is of the order of about 4.4 sigma. The spatial, later on we would see a little bit the localization. The spatial agreement is about this. And the temporal and spatial, if you take all these chance coincidence and everything, if you take into account that it's about 5.3 sigma. The integral Fermi association independently would be about 4.2 sigma. So these kind of tell you, these observations tell you that these independent three observations are actually probably looking at the same event that went on, that happened at 1241 UTC.
What do you mean by the sigma?
What do you mean by it?
Sigma.
What is the significance that you ask the question, what is the probability that this is not by chance?
So it's considering the background?
Everything. It's considering the background. Not only that, you have to also consider how many gamma ray bursts you have looked at in your field of view, and what is the chance that these two events are correlated. They are not independently. So all that. It's not just the background, it's not the detection significance. It is the significance that is the probability which you convert it into significance that these are correlated.
The probability for integral it was more compared to the Fermi, that's it. You want to say the integral and
No. What I am saying is the probability that the integral looking at the same gamma ray burst and Fermi looking at the same gamma ray burst, if you convert it into significance, is 4.2.
okay, so both cases it is around.
They are looking at this. That's what they say, that with this confidence, I am looking at the same event. That's what it means. So this alerted people all over the world were alerted. More than 70 observatories participated in what we call a target of opportunity multi-wavelength observation. So here you see these dots. I don't think you can see all of them. This is space. In space, all the satellites that were going around that we have, and then all the observatories here all over the world have been alerted. And incidentally, this one is in the southern hemisphere, as you saw. So it is in the daytime of southern hemisphere. So people from northern hemisphere observatories, it is extremely difficult to look at them. So primarily the southern hemisphere telescope started observing. It was again in the daytime, 1241. So the optical observatories had to wait for a few hours to look at it. So if you look at the kind of the timeline, so when the gamma ray burst happened in Fermi and integral, the gravitational wave was observed. The optical had to start almost like about 10 hours later, because it was daytime, they had to wait for the night sky to come. And then when the optical observations took place, the SWOP telescope, 1 meter SWOP telescope in Chile, which is a part of the European Southern Observatory, located that there was an optical transient in the galaxy NGC 4993, which is 40 megaparsecs away, or 130 million light years away from us. They located them, since the optical observatories have very high angular resolution, they can locate it to a very high precision. It's about 13 hours, 09 minutes, and minus 23 degrees, the right ascension and the declination. That's how the coordinate systems in astronomy we work with those. And then later on there were many follow-up observations, and I'll come to a few of them. It's almost impossible to cover all the 70 observatories, what they were doing, but I'll pick and choose a few of them to show you the
energy
results.
range also was similar for me and integral?
Pardon?
Energy range? Energy range?
No, this is optical.
No, I'm talking about the integral and the
No, the integral energy range is slightly less. Fermi, it's similar energy range, but it's 20 keV to 10
No, you are
keV.
talking about range, but whatever they have observed where there is a significant peak structure.
But that's you see here. This is their background. This is the gamma ray burst.
So the energy range is not there.
The energy range is this. It's between 10
It
keV
is
to
quite
10
long.
keV.
Integral is a very good
You're
resolution.
saying that
Anyway.
are you measuring the spectrum where it
Yeah.
energy spectrum?
I haven't looked at it very carefully. I can tell you
Integral is
later.
very good resolution.
Integral does have very good angular energy resolution also. Yeah, sure. Okay, so then one could do the source localization. The source localization. So this is the green shaded one would be the one which is from LIGO alone. That is about 190 square degrees in the sky. If you include Virgo, the other gravitational wave observatory, which actually did not see the signal, but they used, because it was occulted at that time, and so they used their information to locate where it could have been, to pin down the source localization. It would be about 34 degrees squares, and this is the coordinates of the LIGO Virgo position. Fermi, which has, I said, about onboard localization about 15 degrees, which is still very, very large, located at somewhere very close to somewhere there. And the optical, which is the best, located it with a 10.6 arc-second resolution to a point somewhere here. And that's what you see. You see here about 11 hours after they see, this is the nucleus of the galaxy, this is the center of the NGC 4993, and here they located that optical transient, and you see 20 days or something, they were days before they were looking at this region, there is really nothing, no transient there. So in the southern hemisphere, there was also the Hess telescope, which operates at beyond 100 GeVs. They got alerted, they started looking at this region, when also again night fell, and these were the pointings they took for maybe quite a few hours, about 15-16 hours. They looked at the three positions of around the source. They did not detect any signal from there. Hess is a high energy gamma ray telescope. It has 5 telescopes, 4 12-meter diameter telescopes, and 1 giant 28-meter diameter in Namibia and in Africa. Let's look at what happened in the other wavelengths very quickly. The near infrared, the UV, and the X-ray counterparts to this were all detected later. For example, I just pick and choose 2 of them. One is Chandra, which uses Volter-type mirrors. It has between 0.5 to 10 keV, so even lower X-rays, lower energy X-rays, and it has a resolution of excellent angular resolution of about 0.5 arc-second. And the other one is, this is the Chandra picture. This is the Hubble Space Telescope, which has Ricci-Kratian reflectors, 2.44 diameters and a large focal length. What they detected was a faint X-ray component was detected by Chandra several days later after the observation happened. The prompt gamma ray emission observation happened, where they say that the luminosity is much decreased. It's about 9 times 10 to the power of 38 arcs per second. So here you see the X-ray component. Here you see the near-infrared component from Hubble Space Telescope. There were other X-ray telescopes which also looked at it much later. There's Swift and New Star. They did not see any X-rays from the region. And however, the UV telescope on the board Swift satellite detected a fading component, so that it kind of detected the tail of the optical emission that was happening.
This is the X-ray one.
This is the X-ray, and this is the optical near-infrared image. So you see they located it about 9 days later, on 26th August. This one is located almost 4 or 5 days later. They located this emission. Now, the spectral features in the optical spectrum, the spectrum is kind of, they claim it is featureless, which has a sharp turnover at about 0.7 micron. And in the near infrared, there is a slow evolution towards the red part of the spectrum. They claim, and I would not deal with this very much because in the later talks this will be dealt more. They claim that these spectral features are consistent with something which is called what occurs in a kilonova. A process which happens is called R process in kilonova during a neutron star merger. But as I said, I would not deal much with them because I just deal with the observations, and the theoretical part would come later in the later talks. This is a simulation of what would have happened if it would have been a supernova. So they claim that this is not a supernova explosion because then the features, the spectral features of a supernova would look like this one. So it is somewhat different from a supernova. Some more about the spectral features. The fact that the X-rays were seen much later and was produced by kind of a rotating highly magnetized neutron star after the merger. They claim that none of the current models can really reproduce this persistent emission which is observed over the time scale of few weeks, couple of weeks or so. And then also they saw is what they measured was that the emission is not on axis but it is off axis, which they claim is that possibly they were looking at, since they are looking at a much later time scale, they were looking at possibly an X-ray afterglow, and not really the prompt emission from when the gamma rays were observed. The radio counterpart to gravitational waves, there are two main observatories, Jansky Very Large Array in New Mexico, in the United States, and ALMA, it's the Atacama Large Millimeter Array. So they look at slightly different wavelengths, as you can see, that one goes from about megahertz, few tens of megahertz to 60 gigahertz. The other, I don't remember, but it's millimeter, so it's different from this would be centimeters, as you can see if you convert this, and this is millimeter. So these large arrays also looked at it later, and what they saw was they did not see any enhancement in the flux in the initial period, but after 19 and 39 days, VLA recorded some flux enhancement. And that's what they claim that from these measurements, they claim that the observations were not really on axis, but they were off axis at an angle between somewhere between 20 and 40 degrees. Let me just say one or two words about the Indian observatories. In India, we have three major observatories which do astrophysics. One is the GMRT, the Giant Meter Radio Telescope. This is in meter waves. So the earlier ones I talked about are centimeters and millimeters. This is meter waves, which look from 50 megahertz to about 500 megahertz. The Himalayan Chandra Telescope, the optical one, it's a 2-meter Cassegrain type optical IR telescope, and AstroSat, which looks at the sources in the sky in UV and X-rays. You can read up some of these, there are excellent websites and some papers on them. None of these Indian observatories detected anything from this event. One thing is that the AstroSat, one of the detectors on AstroSat, which is called the cadmium zinc telluride instrument, CZT, they reported upper limits for about 100 seconds interval centered on the T0 means the gravitational wave event. But the problem there was that the position was occulted by Earth at the time of the trigger. So when they looked at it later also, they did not see any X-ray emission from there. It's not also surprising because CZT doesn't have enough power as Chandra has to locate very faint emission. So it's not very surprising that they did not see anything even later also. From GMRT also only upper limits on the radio flux were possible, and they say that until the count, they probably did not observe as long as or as densely as VLA was looking at it, but they are now keep on observing it at regular intervals in case they want to see, in case some of flux enhancement they see in much lower energies. And also the Himalayan Chandra observation, they took place, but they also did not see any emission or optical emission from the source. Also, there were not the neutrino observatories like IceCube. They had looked at it and they reported that they did not see any events, neutrino events either shower events or muon neutrino track candidates were not present in that direction anywhere. And also the Pierre Auger Observatory, which looks at ultra-high energy cosmic rays, also reported null detection. I think I'm almost at my end, just 1 or 2 slides I have left. So this kind of almost like penultimate kind of slide. What are we going to learn, or what did we learn from these coordinated observations? And these would be the kind of the details coming from the next 2 talks. The neutron star mergers do cause short gamma ray bursts. Here is a picture of the number of bursts as a function of the time of the burst, and you see that they can be classified into 2 types of bursts. One is the short duration bursts and the long duration bursts. Those which are below about 2 seconds are classified as 2-second bursts, and this one was even below 1 second probably. So it's a short gamma ray burst. It's a burst which was also extremely close. This 130 million light years is extremely close to us. In terms of redshift, it's 0.005, which is very close to us. So you have to be really lucky to see that. And it was also faint. It was not really that strong. One could use these information for the measurement of the expansion rate of the universe. GRBs can be used as standard candles that like supernova have been used. We also learned that the speed of the gravity waves is almost equivalent to the speed of light. And another most important thing, this is our process in a kilonova that would produce, you can create gold actually in the universe. This would be the part from details from next 2 talks. Before I end, I just wanted to mention one thing that you may wonder that why do I say all these things, multi-messenger things, from my perspective. It's kind of giving you my own perspective. Some of you were here in 4 years ago when I gave a colloquium here, or even 6 years ago when I was giving a job interview here, and I showed a plot. I don't know how many of you would remember that plot. Is this. That was one thing which I had been working on many years ago, is a neutrino target of opportunity program between IceCube and MAGIC, where if you look at high gamma ray telescopes and other optical laser telescopes, and we would look for the same region in the sky, looking for a correlation between neutrinos and high energy gamma rays, where we were, at that time we were calculating chance probabilities and things like that. And I just would leave you is that in a couple of months there will be one more discovery that will come up, and it's kind of like under embargo, so I cannot leave you with any information, is that IceCube has detected very high energy neutrinos from a region in the sky where both MAGIC and Fermilab has also detected enhancement of flux from a blazar in the northern hemisphere. So you will have to stay tuned for that discovery for next 1 or 2 months. Thank you very much.
When you said that Chandra and Hubble detected some signal from the same region after 90s. Is it
no, Hubble, I have to see.
But yeah, after 90s.
Yeah.
So is it that before that they did not see any signal?
They did not see anything.
Or they looked at only later?
No.
They pointed much earlier.
They had looked at that region many days before, months before, or years before. They do not point to that region normally. They would not. Once they got the trigger, they again pointed to that region and then kept on observing it for regular intervals. And then after 9 days, they saw a faint X-ray.
X-rays only after 9.
Yes, they saw. This is probably comes from the afterglow of the. That's what we will probably talk about it. Oh, you okay? Yeah.
This neutrino observatory doesn't see anything. What does it mean? That it means the flux is low, or
No.
how should I interpret it?
Well,
this IceCube and
I mean,
they're
No.
very optimistic.
one thing you can very clearly say is that if ultra-high energy cosmic rays would be accelerated in gamma ray bursts, this kind of gamma ray bursts, we would produce high energy neutrinos also. That is not the case, at least in this. That's one very easy or quick answer that I can give.
So that in principle should constrain something, some models of this.
No, considering that if ultra-high energy cosmic rays would be produced in gamma ray bursts, if you could accelerate particles to very high energies, they would definitely also produce neutrinos in the hundreds of TeV to PeV energies. And IceCube is sensitive to that, with those neutrinos. The fact that they don't see anything, it tells you that in this gamma ray burst at least, no ultra-high energy cosmic rays have been accelerated or produced at least. That's the only.
But there are
at least
the cosmic ray observatories also.
also Pierre Roger didn't see anything. They didn't see any high energy from there. Yeah. I think at this moment I can say that much. I don't know whether anything more can be done with neutrinos in this part. I don't know.
So can I ask?
Yeah.
So in this Neutron Star marker, so the previous the gravitational plots that we used to see this beautiful
Sure, on the ring down of this. In this
here
case,
you have
this,
only one line and
no, in this case, this was not released or this was not really shown, at least in papers, because I believe that the algorithms that produce that kind of charts are not very well established in the gravitational wave community. In cases of black holes, they know very well what would be the way the chart on everything would happen. But in this case, even though match filtering technique has been used and other techniques are used, I personally, I don't know exactly what happened, but maybe there are other experts. But what I understand by talking a little bit with them is that for the neutron star merger cases, they do not have a very good handle on producing these kind of ring down effects and the chart and everything. That is why they don't release that so easily, or they don't show it out. The other thing you must...
But they can confidently say it's a neutron star.
They can confidently say it's a neutron star.
Without seeing.
Because of the gamma ray burst.
Oh.
Because of the otherwise they would say probably, but they would be very
asking what
it
is
would
the
be kind of more speculative.
So he's asking what is the gravitational wave confirmation.
Yes. Independently.
Irrespective
Well,
of gamma.
independently two observatories saw it. The Hanford and the Livingstone Observatory independently saw the same thing. So that's the kind of, I believe they have a chart and a ring down. It's just that probably it's so dirty and
The
it's
other
not
thing is the pattern matches with
Yeah.
neutron stars merger.
So
No,
you
but
do a match filtering technique.
He's saying that those patterns are not released. They did not release.
No, they have derived the masses of the two components from neutron stars.
From that chart. But they did not release. This time they did not release that.
No, they did not release that. So my understanding is that probably it is just too difficult to do that. The algorithm for neutrons and
It will
neutrons
take some
is
time.
so robust. That's why they did not release it. But definitely they saw in the two observatories independently in Hanford and Livingstone.
The way it happened is that after the first observation by one observatory, all other observatories got the message from that observatory and then they pointed
Yes,
in that
except
direction.
Integral and Fermi. Fermi and Integral, they were looking at it. Fermi has an all-sky monitor. So any gamma ray burst that would happen in its field of view when it is passing through that region, they would be able to see it. For example, here, if it's passing through this region, it would see all the gamma ray bursts around it. So that's why I say independently it observed with having no trigger from gravitational wave.
So,
Similar was Integral. All the other observatories looked at it later. They were told over emails or phones or whatever, there are alert systems set up. You don't need to phone or email anybody. It would immediately, for example, I can tell you for MAGIC, if Fermi sees a gamma ray burst, it gives an alert to MAGIC, immediately the telescope points, if it is night time. Even the shifter who is observing at that time has no control over the telescope at that moment. It just tells you, you sit back, I will be pointing to this gamma ray burst. So there's kind of alert systems, automatic alert systems you set up in most of these. Some observatories do not have these automatic alert systems, so they need to be told and they can schedule observation. That's why some time goes away in that. Few observatories look at it maybe 1 day, 2 days later and things like that.
so only two observatories had to look back into their data and
Right,
find.
right.
there was no simultaneous announcement by two different observations which did not know about each other, but I mean, prior information was there.
There was no real prior information was there in these two observations. They independently saw it, and then they kind of corroborated each other by looking at the light curves and things like that.
And for the Indian observatories, they must have also been alerted.
For example, Astrosat has a MOU with LIGO, where if an interesting candidate would happen, they would send, I don't know exactly if it is, as far as I know, it is not an automatic alert system, it has to be told, and then it has to go through some procedure before Astrosat starts pointing at it. So it would take some time for Astrosat to react. So the target of opportunity is not that robust in place in case of Astrosat, but they still look. In this case, they could not have looked at it also, because even if they got the information, you see that the position of this source, what they call SSS, this optical source, is occulted by the Earth. So they looked at it later, but they didn't see anything.
The other Indian observatories were also by
GMRT,
design they could not see this. Or?
GMRT, you need to again initiate some. GMRT even doesn't even have a TOO program really. So you need to initiate it through something what is called a DDT, which is a director's discretionary time. But GMRTs were, the people were alerted. Since it's such a big event, they knew. So they had reserved some time that if an interesting candidate happens, they would be informed, they would immediately try to schedule observation time for such observations. However, it's not an automatic procedure, so it took some time. But you see that did not make much difference, because there were no radio flux enhancements seen for many days. It was only after 19 days, and one doesn't really know what does it mean, because it's 19 and 39 days, and that also only VLA saw the flux enhancement. Unless we were scheduling observations almost every day for a significant amount of time, and all these observatories are always oversubscribed. So it's a kind of a chance. To some extent, any astronomical event is a chance. It's a chance thing that you see it or you don't see it. The Himalayan Chandra telescope, I don't know really what they were actually looking at that point. I don't know much about it, because they didn't say anything in any paper. At least there are some papers where they reported it. This is only what is called the GCN circular. It's a circular which you give to people that we have looked at this source at this time. So I don't have any information about really the Himalayan Chandra telescope. That's the only information you can find in the web or anywhere.
Well, we are picking up new applications, DDT something. Okay, so I think we should thank Pratik for the